In our previous lecture, we defined the magnetization vector and we derived for a special case whenever there was no source or the current density was not there in the region, then we found that a magnetic material placed in a magnetic field which gets magnetized because of it can be represented by equivalent magnetic charge densities. And I also told that those magnetic charges are fictitious in nature. They are just mathematical construct to solve the problems. However, as you know from Maxwell's equation, that the source of magnetic field are currents. So I have mentioned at one point that this magnetization problem can be solved by equivalent current densities. Now let us see how to formulate and how to see how a magnetized material can be represented using equivalent current densities. So as defined in previous lecture, that magnetization vector was equal to the dipole moment, magnetic dipole moment per unit volume. And this is actually an averaged quantity, means we are not considering the changes within like an atom. Like in an atom there is a nucleus and there may be electron cloud and all those things, so there is some kind of non uniformity there. But if we take a scale which is having dimensions much more greater than a single dipole moment, then we can take an average picture, and this average picture is being considered in this magnetization vector, and this is the number of dipole moment per unit volume. So this is the definition of magnetization vector, that is the number of dipole moments. If we add them and divide with the total volume, then we get the magnetization vector, which is just the volume density of magnetic dipole moment. So you see this dm, the small magnetic dipole moment, can be represented as m dv. Now you know that we have derived the vector potential, magnetic vector potential, due to a magnetic dipole, which was simply given as mu naught m cross ar over 4 pi r square. Now, for this m to be replaced with small magnetic dipole moment dm, I can replace this by this quantity. So, dA due to a small dipole moment in terms of magnetization vector can be written as mu naught m cross ar. Now, to avoid any confusion between source quantities and the field quantities, that is the observation point and the source point, I am using this prime or dash to represent the source quantities or source points over 4 pi r square. Now, you have seen in our lecture number 23 that gradient of 1 by r with respect to the primed coordinates is simply AR over R square. We have derived gradient of 1 by R with respect to unprimed coordinates, and it came out to be minus of AR over R square. So this is very easy. If you do not know how to derive this, just watch my lecture number 23. It is just simply the gradient with respect to the prime coordinates, where R is simply x minus x prime square plus y minus y prime square plus z minus z prime square. So if you take the gradient of this quantity, you will get this quantity. Okay, so I can write by using this in this equation this small magnetic vector potential as mu naught m over 4 pi cross del dash 1 by r dv dash. So there is a reason that we are trying to convert and include the del operator somehow. We will see why we are trying to do this. So the total vector potential due to all the dipoles in the magnetized quantity is A is equal to the integral of dA over the whole magnetized volume is equal to mu naught upon 4 pi. It is a constant, so I have taken it out of the integral m cross del dash 1 by r dv dash, where integral is over the whole source volume, that is the magnetized material, which we are now representing as consisting of small dipole moments, and those are magnetic dipoles. Now there is a vector quantity which we have utilized at so many places, del cross f, and a vector g is simply del f cross g plus f del cross g. So I will utilize this. So I can write del dash cross m over r is equal to del dash 1 by r cross m plus 1 by r del dash cross m, or this quantity is equal to minus of m cross del dash 1 by r plus 1 by r del dash cross m is equal to del dash cross m by r. So I will take it on LHS and take this on RHS. So m cross del dash 1 by r is given as 1 by r del dash cross m minus del dash cross m by r. So I will put the value of this m dash cross del 1 by r in the equation of the magnetic vector potential. So this quantity I will place here. So I will find that the magnetic vector potential now can be written as A is equal to mu naught upon 4 pi integral over the whole volume, the source which where it is there, del dash cross m over r dv dash minus mu naught upon 4 pi integral over whole volume v dash del dash cross m by r dv dash. Now there is a vector quantity which we can derive easily, and we will derive here itself. What is that quantity identity? That is del dash cross f dv over a volume v dash is equal to minus f cross ds, where that surface is enclosing the full volume. So it is similar to, identity similar to the what we can say, some kind of divergence theorem, but it is not exactly that thing. But it is similar to that the we are trying to convert a volume integral into a surface integral. So this is the volume and this is the total surface which is enclosing this volume. So if we just calculate this integral on the surface is equivalent to calculating this integral inside the whole volume. So we now want to prove this identity so that we can utilize it somehow in our equation of this magnetic vector potential. So to derive this, let us say that there is a constant vector c. This vector is a constant vector. Okay. Now let us take the divergence of this vector. Now this f cross c is a vector over a volume v dash dv dash. Now I can use the theorem directly here and convert this into a surface integral. Now there this is just a divergence theorem, nothing else. So it is simply f cross c dot ds dash over whole surface s dash, which is enclosing this volume. Now you know that a dot b cross c is equal to b dot c cross a is equal to c dot a cross b. Now we want to somehow make this equation in a form that we have c dot some quantity on this side and c dot some quantity on this side, because c is a constant vector. So this equality sign will imply that these quantity in the vector in this bracket are equal. So we want to somehow get this form of the equation. So let us say this is A, this is B, and this is C. So we will cyclically change them. So it will be equal to F cross C dot ds dash is equal to, now F can be converted to C cross C can be converted to ds dash dot, and ds dash can be converted to F is equal to, now this C can be converted to ds dash cross, now this ds dash can be converted to F, and this F can be converted to C. So I can write it as C dot ds dash cross F is equal to minus of C dot, and I will just change the direction of this cross product. So this is F cross ds dash. Similarly, I will try to formulate it here. So I can write this del dash cross F cross C is equal to, let us say this is A, this is B, this is C. So this will be converted to F dot del this is C cross del dash equal to, now this can be converted to C dot, and now this C can be converted to del dash cross, and this can be converted to F. So you see these two can be now replaced with, this can be replaced as C dot del cross F dv dash over a whole volume v dash is equal to this quantity minus sign C dot F cross ds dash over the whole surface s dash. So since this is a constant vector and this is a dot product and it is equal everywhere, so we can write from this equality that this uh, del cross F dv dash over the whole volume v dash is equal to minus of F cross ds dash over the whole surface s dash. So this is the quantity which we have proved. Now we will utilize this. Now you see that we got the equation of magnetic vector potential as mu naught upon 4 pi over whole volume v dash del dash cross m over r dv dash minus mu naught upon 4 pi over whole volume v dash del dash cross m over r dv dash. Now this is f, function f, and this is del dash. So I can utilize this quantity now like this. So I will replace this with this. So a can be written as a is equal to mu naught over 4 pi. I will just keep this term as same, del dash cross m over r dv dash. This minus sign will get cancelled out, so mu naught over 4 pi, and this will be now converted to a surface integral over s dash. F is now m by r cross ds dash. Now ds dash is always pointing in the normal direction to the surface, or this is an, the normal vector to the surface. So I can write it as a is equal to mu naught over 4 pi del dash cross m over r dv dash plus mu naught upon 4 pi m cross an dash ds dash over r. This is over the whole volume v dash, and this is over the whole surface area s dash. This is the closed surface area. Now you see that from the vector Poisson equation, this is equivalent to a solution with a volume current density equal to this and a surface current density equal to this. So I can replace these two, and I can write the equation as A is formed of due to two quantities, mu naught upon 4 pi J volume current density dV dash over R over whole volume V dash plus mu naught over 4 pi. This is surface current density Js over R ds dash over whole surface S dash, enclosing a volume. Now it implies that a magnetized quantity or item can be replaced by an equivalent current density, where there is volume current density equal to del dash cross m and surface current density equal to m cross an. So this is the mathematical derivation. Now we should know how to have a physical intuition or the physical meaning of this thing. So you see that let us assume this is a material of magnetic material, and I am just showing some part of it, and I am assuming that it is magnetized with magnetization vector out of the paper. So it implies that the magnetic dipole moments should be like this in this quantity, in this material. So these should be like this, and the current direction should be like this. So because of this, they will create a magnetization which is in the direction like this out of the paper. Okay, so in this way, these are small dipole moments. So you see that if this magnetization is uniform, then all these dipole moments are equal. So inside, these being currents in opposite direction, these will cancel out, this will cancel out, this will, everything will cancel out, this will also get cancelled out. So inside volume there will not be any equivalent current density. However, on the surface you see that there will be a current flowing in this direction on this side, and in this direction on this side. So you see that on this surface there is a current density which is equivalent to surface current density, which is flowing in this direction. However, inside volume there is no current density, because for volume current density to be there inside the volume, this should be not equal to 0. Since this is uniform, so this is equal to 0. So that's why our equation is also showing the same thing. Now we need to find whether we have taken the correct sign. We can just verify it mathematically. So the current density is given as M cross AN. Now for this curved surface area, AN will be in this direction. This is AN and M is in this direction. So you see M cross AN will be in this direction. So again we got the correct sign by physical intuition. Similarly for this side, AN will be in this direction and M is in this direction. So M cross AN will be in this direction only. So again this side also we have got the current direction correctly. So this is how we can physically also think that any magnetized this item material can be thought of as formed of equivalent current densities. That, and if the magnetization is not uniform, then there will be a resultant current density inside the volume also, and this will not be equal to 0 in that case. So there will be effects of both the volume current density as well as the surface current density, and it will imply that this M, the magnetization vector, is going to have variation with respect to the space coordinates, and because of that the internal atomic currents will not be able to cancel themselves each other, and there will be a net volume current there, or the not volume current density will be there in that. So although we could have derived this equation while starting from the classical atomic model and using some little mathematics, but the results will be similar. So instead of going into intricate mathematics, we should just understand how to derive this equation on the lines which is very similar to what we have done in the electrostatics case for the dielectrics. In that case we got a volume charge density equal to minus del dot p, and a surface charge density sigma s or rho s equal to p dot an. So we got these two quantities similar to what we have seen in the case of normal dielectrics in the electrostatics case. So you see that the things are although very little different in terms of this scalar and vectors and cross and dot products, but physically intuitively the things are quite similar in both of these cases. Now, in the next lecture, we will solve a numerical example based on this concept. So, if you find that this lecture is helpful to you, then please share and subscribe our YouTube channel, and also join our Telegram group whose link is given in the description of this video. Thank you.